Welcome to Maths with Bob. This is actually series 3 in the substitutions and integration series, and you can see here we've got some trigonometric and hyperbolic substitutions. So basically in the integrand you're looking for like a squared minus u squared, or a squared plus u squared, or u squared minus a squared, and you can actually use these substitutions. Obviously you need to change the bounds, obviously, if you're going to do a substitution if it was a definite integral. Now, a lot of cases you'll find that even the quadratic denominators, when you complete the squares, and they'll be able to form one of these type of substitutions, and I'm just going to show you that in a second. Okay, well, with the quadratic denominators you may be able to actually form them into like a u squared plus or minus this capital A squared, and then use the previous substitutions. You might remember to complete the square, we just remember you always go, if it's x squared plus say bx, just remember it's always equal to half the coefficient, so it's x plus b on 2 all squared. Okay, it's actually just, that x doesn't look too good. It's actually, okay, x plus b on 2 all squared, and then you always have to subtract off b on 2 all squared. Now, okay, that should be trouble here. Pen square. Now, obviously, if this is a plus and a minus, okay, you have a plus and a minus here. But this, even though this may be a negative here, when a negative squared, it actually will turn to positive. So I always just say, just always subtract off b on 2 squared. Actually, all right. Okay, let's do an example. Okay, well, here you can see example 1, the integral of the square root of a squared minus u squared du. Now this is suggesting that we use that substitution u equals a sine theta. Okay, so let's do, so we let u equal a sine theta, and just get an expression for du. So du would equal what? D sine is a cos theta d theta. Okay. Or if you like, du d theta is a cos theta, just multiply both sides by d theta. Okay, so we're going to substitute a cos theta d theta. So let's go ahead and do the substitution. You can see here this would be equal to what? The square root of, okay, what? A squared minus, now it becomes a squared sine squared theta. And okay, du is now a cos theta d theta. Okay. Okay, shorten this a bit. Okay, all right. So obviously we can see we can simplify the integrand now quite nicely. Take an a 1 minus sine squared, which is cos squared. So it's just take this becomes pretty easily to see. This becomes what? A cos theta by another a cos theta d theta. Okay, that's simplifying, and you can see what's happened. We've actually simplified that square root nicely. Okay, now we end up getting what? We end up getting what? A squared, which we could take out, and a cos squared theta d theta. Now we're going to have to do the cos squared theta substitution from our double angle results, and you might remember that is a half 1 plus cos 2 theta. So I'm going to basically continue shortly, or I'll just rub this out and we'll continue again. Well, okay, we've actually done the substitution and transformed the integral, if you like, to a squared integral cos squared theta d theta. Now, how are we going to do this integral? Well, we need our double angle results, I guess, for cos squared theta. And what is cos squared theta? Cos squared theta is equal to, you might remember, a half 1 plus cos of 2 theta. So we need to basically do that substitution for cos squared. Okay, so basically this obviously needs to pop into here. And so basically we end up getting what? Let's have a look. Okay, we have, okay, first up, a squared on 2, integral, okay, we need 1 plus cos of 2 theta. Okay, d theta. Okay, now obviously we can see that this is just going to be equal to what? A squared on 2. Now this would be a theta. Now when I integrate cos, I come back to sine, and I'll get a half sine of 2 theta. Okay, now I get write that half sine of 2 theta. Now sine of 2 theta is actually 2 sine theta cos theta. There's a constant here. Eventually we'll need to pop in. Okay, so we need to first of all simplify this a little bit, and we are. You'll see in a minute when we, because sine 2 theta is 2 sine theta cos theta, we're going to need an expression for cos of theta. Okay, so let's actually do this. Okay, we're going to equal to a squared on 2. Okay, theta, we have a half times 2, so it's obviously just 1 sine theta cos theta. Okay, now we're going to, I always say it's best to probably draw up the triangle for the substitution. Okay, so here we have a triangle. Okay, and we know that what sine of theta was equal to what u on a. Okay, u on a. And then we know that obviously this side here, the adjacent, is a squared minus u squared. Okay, so we now need to basically put the substitutions in. A squared on 2. Now theta is obviously what? Sine to the minus 1 of u on a. Okay. Now plus sine theta. And we know it's just u on a. And what's cos theta? You can see here it's the square root of a squared minus u squared on a. Okay. Plus c. Okay. We can simplify this slightly. Well, there's not much to do really. I might just leave it like that for the first example. Okay. All right. Thank you. We'll just work on example 2 shortly. Well, here we have example 2, dx over the square root of x root 4x squared plus 9. Now, what substitution will we use here? So we're going to have like a u squared plus an a squared. Okay, so u would be actually equal to 2x, and the u squared plus a squared. Okay, so we go, let's have a look. Okay, so we know u is 2x, so 2x would equal a tan theta. Now, a you can see here is 3, square root of 9, so it's 3 tan theta. Okay. Now the idea obviously is to get like a perfect square underneath the square root so that it will simplify. So here we'd then go, okay, this is 2 dx is equal to what? 3 sec squared theta d theta. Or if you like, 2 lots of dx d theta is equal to 3 sec squared theta. Okay, just multiplying both sides by d theta. So you can see here, in fact, dx is actually a half of that. Okay, so let's actually now substitute it all in and see what happens. So we'll get what? Dx is in fact what? Half of that, so it's basically going to be 3 on 2. So let's actually start substituting it in. So dx would be what? 3 over 2 sec squared theta d theta. Now, okay, what is x? Well, x you can see here is basically, if you look at the substitution, just 3 on 2 tan theta. Okay, and the square root of this becomes what? Let's have a look. Okay, the square root of 4x squared, okay, which is what? 9 tan squared theta plus 9. Okay, obviously we'll be able to take a 3 out of that. 1 plus tan squared is sec squared, so that will be simplified too. Let's actually just simplify that too while we're here. Okay, so let's just simplify this expression. Okay, so what would that simplify to? Well, remember we took the 3 out, and 1 plus tan squared was sec squared, and in fact we have to take the square root of sec squared, and we should just get sec theta. Okay, all right, now okay, so a few things will cancel. We can see straight away a couple of things to cancel. The 3 on the 2 and the 3 on the 2. One of the secs. Okay, so we then have what? Sec on tan. There's a third at the front. Okay, so let's actually just rewrite this. Well, okay, well now I've just written it as minus 1/3 ln cosec theta plus cot theta. Okay, now the problem is we don't actually have an expression for cosec theta or cot theta, so this is where we always draw up the triangle. So let's draw up the triangle for the substitution, and we'll put the angle theta in. We know its tan is 2x on 3. Okay, it's a right angled triangle. We know the hypotenuse must be what? 4x squared plus 9. And let's just substitute this in. Okay, so we end up getting what? Minus 1/3. Okay, ln. Now cosec. Okay, cosec is 1 on sine. So sine is 2x on that, on the square root of 4x squared plus 9. So it's the reciprocal of that, which is the square root of 4x squared plus 9 all over 2x. Now cot is obviously the reciprocal of tan, so it's now just 3 over 2x plus c. You can see here we could just add the numerators there, but at this stage we just leave it as it is, and you can see here the triangle being very important to try and get some of these other values. Okay, well here we have example 3. We have x plus 5 dx all over the square root of 2x squared minus 7x plus 3. Now the first thing we do when we look at this integral is we can see there's a square root, and we need to actually compact that. So we are going to need some sort of substitution, and you can see it's a quadratic, so we're going to have to complete the square. So the first thing we need to do is look at that 2x squared minus 7x plus 3 and try and complete the square. Okay, so let's actually just complete the square. So first up, okay, so we have 2x squared minus 7x plus 3. So this is complete the square. Okay, so first I would just take a 2 out. Okay, what have we left with? X squared minus 7 on 2x plus 3 on 2. Okay, we can then just complete the square on the x squared minus 7 on 2x. So it's going to be 2 lots of, okay, x now minus half that coefficient, so 7 on 4. Complete the square. Subtract off the extra part which you created, which is minus, so going to be 7 on 4 squared. Okay, technically that's minus 7 on 4 squared, but when we square it, it's going to be positive anyway. So I just like to write it as minus 7 on 4 squared, and then we add on 3 on 2. Okay, right, so we need to basically try and, what's that, 49 on 16, and that's 24, so it's going to be 25. Okay, so it'll be something like this. 2 lots of x minus 7 on 4, okay, all squared, minus 25 on 16. Okay. All right, now we're going to have to let u equal, okay, a few things we're going to do. Okay, let u equal what, x minus 7 on 4. Straight away you can see that du is actually equal to dx, and you can actually see that u plus 7 on 4 is equal to x. Now the other thing is we have actually an x plus a 5 in the numerator, so x plus 5, so all we do is just go like this, pretty easy. So we just add 5 here, and add 5 there. Okay, so we now have an expression for x plus 5. So what's x plus 5 is going to equal, what's that, u plus about 27 on 4. Okay, that's the substitution we're going to plug in for x plus 5. Okay, so let's actually do this conversion now. Okay, well, I've done the substitutions here. I'm going to pull this integral apart and do each of the bits separately. So let's actually, first of all, let's have a quick look. We're going to take a root 2 out, so we're having 1 on root 2 integral. Now we're going to have a u over the square root of like a u squared minus an a squared, and the a is actually just 5 on 4. And then I'm going to separate that with the 27 on 4. We can actually take that out the front as well in a minute. And that's going to be on the square root of u squared minus 5 on 4. And this is where we're going to have to do the trig substitution here. The other one is actually going to be turning into a standard integral that you can see here. The u on the top is quite nice because it's a derivative, or the constant multiple of the derivative of u squared, okay, with a du here. So we're going to actually first of all, we're going to first up look at each of these integrals one by one. So we're going to look at this one first, okay, which is a standard integral, that's already. But the trouble is, this one here, we're going to have do a trig substitution for. Okay. So let's actually look at these individually now. Okay, well, let's actually start to pull it apart. Okay, we're going to have to use another variable now. Let's let p equal, u squared minus 5 on 4 all squared. Okay, we're going to do another substitution. Okay, you can see here that what? dp du is actually 2u, or dp is equal to 2u du. And we've got a u du, so obviously the u du is just a half of dp. Now, I've got a 1 on root 2 at the front as well, so we may as well actually just complete this integral. Okay, so what happens now? Well, you can see here the u du is a half, so I'm going to have this is going to equal 1 on 2 root 2. Now we have this is going to turn into u du is you can see here we've taken the half out, so it's actually we just have a dp left, and we have p p to minus a half dp. So this is, as you can see here, is a reasonably standard integral, and we'll complete this. Okay, so obviously what do we do now is we are going to add 1 to the power, so we bring it up to a half. It's all over half, so we have 1 on 2 root 2 times 2 on 1. Now we actually have what? P to the half. Okay, so it's just going to be what? P to the half. We have a c as well, but as you can see here, we're just going to now cancel, and we'll just sort of, the 2's here, p to the half, we know what p was, and we know we can actually eventually go back to x through the u substitution. So we'll just try that. Okay, now we've got the second substitution for p equals u squared minus 5 on 4 all squared. We eventually can actually simplify this integral, okay, with the 1 on root 2 as well. We eventually get, we should get what? 1 on root 2 p to the power of half from before, and now we have to go back and try and work out what this is. This is 1 on root 2. Now the first thing is we put in p, okay, so it's going to be the square root of, now p is actually u squared minus 5 on 4 squared, and u is actually equal to x minus 7 on 4. So it's going to be x minus 7 on 4, which is the p squared. Now p is equal to, you can see here, u squared, and the u is actually equal to x minus 7 on 4, I should say, and then we have a minus 5 on 4 all squared here. So we need to simplify this in terms of x, so we need to expand that out, okay, and we end up getting what we get, 1 on root 2, the square root now. We get x squared minus 7 on 2x, okay, plus 49 on 16 minus 25 on 16, so it's x squared minus 7 on 2x, and then it's just plus 24 on 16. Now we could, so 24, oops, 24, that's supposed to be 24. Let's try to go back a bit. X squared minus 7 on 2x, okay, plus 24 on 16. Now, okay, so we could actually take a 16 out and try and simplify that a bit, but at this stage I'm just going to leave that first integral just like that, and then we're going to start to work on the second part now. And the second part is really what we want to look at. This is the actual trig substitution here, but you can see here we have to do a fair bit of work just in the beginning stages just to try and simplify. We've done the first part, now let's look at the second part. Now I'll take the 27 on 4 out, so we're going to get 1 on root 2 multiplied by 27 on 4, integral now du over, you can see here, square root of u squared minus 5 on 4 all squared. Now this is where we're going to do the trig substitution, and we're going to let u equal a sec theta, and so we're going to let u equal, a sec, which is a is 5 on 4 sec theta, du, you can see here is 5 on 4, differential sec is sec theta tan theta d theta. So that's the du substitution. Okay, and then we're going to plug it in and try and simplify this. Now, you've got a u squared, so we actually have a 5/4 sec squared theta. So let's actually, let's actually put all this in. Let's see what happens. Okay, we're going to get what? 1 on root 2 by 27 on 4. Now, du was 5/4, so there's going to be a, let's take the 5/4 out, 5/4, and there's going to be an integral. Okay, du is now sec theta tan theta d theta. On the bottom we get the square root of, what's that, 5/4 sec theta all squared minus 5/4 all squared. Now, on the bottom we get, 5/4 sec squared theta minus 5/4 squared. We can take a 5/4 out. Sec squared theta minus 1 is tan squared. Then we can take the square root of everything. So we end up getting, on the bottom down here, we'll get what? A 5/4 and just ordinary tan, because it's the actual square root of tan squared, tan theta, now in the denominator. Now, we'll be able to cancel a few things, so let's actually just cancel a few things. Okay, so first up, 5/4s cancel, tans cancel, and then we end up with the integral of sec theta. So actually, let's simplify that bit a little bit, and you'll see there's a really big space between the sec theta and the d theta. Now, this is for the factor, which is a bit of a trick, I guess, for sec and cosec, the easiest way. We could do it by parts, but I think the easiest way to do cosec and sec is just multiply by this factor, sec theta plus tan theta over sec theta plus tan theta. Okay. Okay, a bit of a trick, I suppose, for these two integrals. But now you can see here we have a sec squared theta and a sec theta tan theta, which is the derivative. Well, the top is the derivative of the bottom, and it's now going to turn into a log for us. Okay, so let's have a quick flip. So what is it going to be? Okay, this is going to equal, what, 27 on 4 root 2. This is now going to be the ln of, sec theta, sec theta plus tan theta, sec theta plus tan theta. Okay, we have a constant eventually on the end. Okay, so now, what do we need to do now? Well, first up, we've now got to try and get expressions for, we know what our substitution for sec theta is. We need an expression for tan theta. Okay, so we're going to need to draw up the triangle. Well, okay, we're just about there. Let's draw up the triangle now. Okay, we have theta. Okay, now we know sec theta is u over 5/4. I'll just write u over 5/4. I mean, I can simplify this a bit better, but we just write this as square root of u squared minus 5/4 all squared. Okay. Okay, so now we need to substitute this back into sec theta and tan theta, and we know what sec theta is, and let's actually have a quick look. So this is equal to 27 on 4 root 2 ln sec theta is u over 5/4, and u was what? X minus 7 on 4 over 5/4, which we'll simplify this in a minute. Okay, and plus a tan theta. A tan theta was, if you have a look at this triangle, it's a square root of u squared minus 5/4 squared all over 5/4, so it's going to be what? 4/5, the square root under here, u squared, which would be x minus 7 on 4 all squared minus 5/4 all squared. Now, we're going to actually try and simplify this. I'm running out of space here, but we'll try and simplify this and tidy up shortly. Second part of the integral. Okay, you can see a few things we could do. Just go, 27 on 4 root 2. Okay, ln, we could write that as, let's actually just write that as 4x minus 7. Okay, we'd write this as 4x minus 7 on 5. The 4's would cancel. Okay, we'd write this as, 4 on 5. Okay, and then we can try and simplify the expression inside there as we did before for the other part, and that turned out to be the same as the other part, so it would be, let's have a look, 4 on 5. Okay, and that was the square root of, you can see here, x squared minus 7 on 2x plus 24 on 16, which we could actually write as, okay, what, 3 on 2, actually, if we wanted to. Yes, okay. So we could tidy that up slightly. Okay. So let's actually finalize the integral. So eventually it's going to equal that part plus that part, okay, plus a constant of integration. We can sometimes bring in the root 2's if we wanted to, but I think as it's a fairly long question, we'll just leave it as it is at the moment, and I'll just tidy up shortly. A few things, but basically you can see that this is a fairly involved example using multiple substitutions and multiple ideas to break up integrals and resubstitute and break them up and resubstitute. Okay. Well, thank you for watching. Bye for now.